Hi. So, wrapping things up, we'll look at thermal loading, pressure vessels, torsion experiments. This is a rough screencast of the lecture. Not a special version. Hopefully this will be good enough I can post this online. So the things that we need to wrap things up are thermal expansion, pressure vessels, and the torsion equation. Thermal expansion, straightforward, just a single equation to look at. So we know that most things, when you heat them up, they tend to expand. How much they expand by? Well, that depends on the properties of the materials. We're not so obsessed by the physics there. So in terms of engineering, we can usually define a coefficient of thermal expansion which will be independent of temperature pretty much, and we'll define this as the amount something expands in one direction in terms of how much temperature it's got, and so it would be, well, actually it's strictly speaking it's the strain divided by the temperature difference, but it would be the amount it expands divided by the temperature it changes and the original length. So nice way to define that would be to say strain per degree rise in temperature, although you probably wouldn't find it quoted like that in the books. So normally in the books it comes in this form. So the change in length of, say, we imagine a long bar, so we've got a long bar there, it's going to be related to the change in temperature multiplied by this constant here. The fact that this constant is a constant, of course, is non-trivial. And for ferrous metals, so for iron, for example, it doesn't expand much, nor does mild steel, so that would kind of imply that perhaps these are good metals to work with if you want to have changes in temperature. That's not true, because say something like cast iron, you certainly don't want to be taking that down to cold temperatures. It becomes very brittle. And then we've got aluminium, which seems to expand a lot in contrast with iron, and yet you can make your planes out of aluminium, of course, and not iron. Of course, there's a question of density there as well. So this is how we're going to use this thermal expansion equation. We're going to take the L, divide through, and so we'll have delta L over L, and we've seen this before. We know that's our definition of strain. Since this is related to thermal changes, we'll call this thermal strain. We'll give it a subscript T. So we've got strain subscript T. So I can heat things up and they'll expand, and we're going to get some kind of thermal strain appearing. This is a classic one to think about. What would happen if I have a nice big copper plate and a hole in the middle there? When I heat it up, would I expect the hole to, I don't know, stay the same? I suppose one would be one option. The other one would be that it would expand outwards. And since we're expecting everything to expand, it seems to make sense that perhaps we'd expect the hole to get smaller. So which do you think it's going to be? Stay the same, bigger hole, or smaller hole? The answer is the atoms will always, if you heat them up, always want to be moving away from each other. So if they're wanting moving away from each other, that means that they can't actually make a smaller hole, because then they'll be contracting and getting closer to one another. So the result is that the hole is going to expand in this particular case. Show an example of us applying the term, the coefficient expansion term. So here we've got a 2 meter long aluminium bar, so it's 2 meters. It's going from 20 degrees up to 220 degrees. So our change in temperature is going to be 220, take away 20 is 200. We look up our value for coefficient of thermal expansion, and that's 24 times 10 to the minus 6. And it's got a length of 2. So the overall change in length will be 9.6 millimeters. So that's straightforward how to use the equation. This is in terms of structural stress analysis, this is the typical kind of scenario where we would be interested in thermal expansion and thermal strain. We can imagine that we've got maybe 2 pillars and they're fixed, and that we've got some kind of steel rod in between the two of them. In this case I'm using an aluminium rod, but normally maybe a steel rod, and that's maybe a part of the support structure, or maybe it's an aircraft, so we have an aluminium bar in an aircraft holding 2 things together. What's going to happen in terms of heating this up? So I expect that that bar will want to then push against those 2 pillars, and it's going to create some stress. So sure enough, we're going to go and work out first of all what the thermal strain is. The thermal strain is just dependent upon the coefficient of heat expansion for the material, the aluminium, and the change in temperature. That's all we need. Okay, so we got alpha times delta T, so that gives me the strain. Now all I have to do is look up what Young's modulus is, and then I've got, well, this is an equation rewritten for Young's modulus is stress over strain, so therefore it follows that the stress is going to be Young's modulus times strain. So that's me rewriting that equation there. So the stress is going to be simply the Young's modulus multiplied by the strain, which gives us this amount of stress. Let's say I'm interested in the force being pushed against the column, because I'm doing some further structural analysis. I would then have to take my stress, multiply it by my area, which I'll look up from the diameter of the bar, so I use pi d squared over 4, and that will be my the way I'll work out the area. Multiply those two together, and I find that I get a force of basically about 660 kilonewtons. What about the a case where we have an increase of the length of a 1 meter long aluminium bar, and we're going to heat it from 20 degrees to 120 degrees. So this is very similar to the problem before, but the problem before I did was 2 meters long. So this is for you to have a go and see what you think. So the correct answer there was 2 millimeters. So let's just check that. So we've got 1 meter bar times by 200. No, sorry. Oh, yeah, the other thing I changed there, didn't highlight it, was the change in temperature has changed down to 20 degrees to 120 degrees. So we've got change in temperature of 100 degrees times by my 24 point minus 6 thermal expansion times by my length, and that gives me, can you see there, 2.4 times 10 to the minus 3, so that's going to be in meters, so in millimeters 2.4. So we'll repeat the problem, and this time I'm going to have a 1 meter long bar. I'm going to go back to heating it from 20 degrees to 220 degrees. What's the force now going to be in this case? Okay, so this is a trick question, because we've now made the bar a 1 meter long bar, and what's happened is that this is redundant information. We don't need to know it in terms of the strain. Strain is change in length divided by original length, so we don't need it there. So our strain doesn't change. Young's modulus doesn't change, obviously, so that's not going to change. And our area is not going to change in. The length doesn't affect the diameter. So the force was exactly the same result that we had before. So that was a trick question. Stress and strain in more than one dimensions. We're only really interested in when we're doing stress and strain in 2 dimensions. So here, let's imagine what would happen if I have an object. I'm trying to pull it apart in the y direction here. So it's being pulled apart, and what happens is that it shrinks in from the x direction. So the y direction, we've got a change in y. Okay. Now I'm going to divide that by the original y length, and that will be my strain in the y direction. And again, imagine what's going to happen here. We've got a change in the x direction as this goes in. Okay. Divide it by the original x length, and so you can see that we're going to have a change in the strain in the x direction. This value will be positive. It's y is getting longer. This value here, say it's a column, it's getting shrinking a little bit, so it's getting smaller. So this is going to have a negative value. So Poisson's ratio is defined as the negative of the ratio of the strain that's been kind of squeezed in and the strain that's been pulled out. So that's going to be the bigger strain we expect than this strain here, and that's be slightly smaller. And indeed we find values of typically about 0.3. So we always and if the volume, because you've got to imagine this is going to be potentially 3D, so we have the x coming in, and we'll have the other component, which would be the z component. So that would come in. So we've got 2 sides effectively coming in with a 3D object, and it turns out that something like rubber, which wouldn't lose its total volume, or lead is pretty much getting there as well, doesn't lose its total volume. Then you get a lateral strain divided by a longitudinal strain of 0.5, okay, and that's because the strain is coming in from one side and from the other side, so it's not, you might expect 1 if the volume stays the same. It's actually 0.5. So values typically vary from 0 up to 0.5, and for metals they hang around about 0.3. So what does this mean? So in terms of strain, it's telling me that the Poisson's ratio is saying that if I pull something apart, I expect strain to be happening in that direction. So that's this part of this equation. But I also, if I'm going to squash something, then I expect it to be, it's going to, like a balloon, it's going to go in the opposite direction and get bigger. So if I squash something in there, so in this particular case, if I'm pulling it apart, okay, and then if I try and squash it, so I make my stress negative, so I make that a positive value, that will have, so we've got minus times a minus, positive, that will have the behavior that this x will get bigger, okay, and it get bigger by the Poisson's ratio. So the strain value when we're working in 2 dimensions will be a combination of the stress being applied in the x direction and the stress being applied in the y direction. Now those 2 equations, we're ignoring the z direction, but notice we've got sigma x here, and we've got sigma y here. So I could rearrange this. So equation 1, equation 2, I could make my equation 1, substitute it into equation 2, and for example will get rid of sigma y. Okay, and then I'll be ending up with a strain x and a strain y equation, and when we do that rearrangement we get these two equations. So that we're doing that for sigma x and we'll do it for sigma y. So the alternative is maybe if I'm blowing up a balloon and I look at how it's changing in the one direction there, the x direction, and how it's changing in the y direction there. I can then go back and work out what kind of stress is occurring in the x direction by using this equation. So this would be if I had strain gauges and I was doing something a bit more complicated. The reason why I'm talking about this is because we're going to need it for the next piece of apparatus we're going to look at, which is a pressure vessel. So for our pressure vessel, what we're going to do is we're going to imagine that as we blow up the balloon, that the balloon will move, there'll be some sort of stress that's making the balloon want to go off in this direction, and it will, as I'm blowing up the balloon, there will also be some sort of stress that's making it go off in this direction. This is what we're going to be analysing next. Okay, so there's a repetition there, I ought to get rid of it. We're not going to look at 3D stress equations, but it's quite straightforward to extend the 2D example we've just given there onto 3D. That's not a big deal. So for example, if you was looking at how we'd expect something to change in the x direction, well, we would expect that if I apply stress in the x direction divided by the Young's modulus, it's going to go off, get bigger. Then if I try and squash it, so I need to put a negative sign there, subject to that we're going to get reduction due to the Poisson's ratio, we would expect that we were going to have a y there, sorry, and a z. Okay, so if I'm now trying to squash it in the y direction and the z direction, then I expect my x direction to be going off, but not as efficiently as it were if I was trying to pull it in that particular direction. So pulling, if you like, is better than squashing. That's what we're saying. So in practical situations, this is a plane stress example, and it's the 2D example we've been looking at, and we've assumed that there's going to be no stress in the z direction. However, this means that there is not necessarily change in movement in the z direction. Okay, so the classic examples here is thin things. Thin things cannot basically have stress in it. So if this is like a membrane, imagine my palm to membrane, this can't handle any, if this thinner I make this actually a paper, for example, if I try and push a paper, then it's automatically going to deform. So therefore, something like this, like a paper, cannot have any stress in its sort of normal direction. The stress for me to be pushing here, I'd have to be pulling it tight to stop me trying to push in this direction. And what might happen is that as I'm pushing, this paper is going to potentially move. So it will potentially get some movement, but it won't have actual force going in that direction. So this lets us move on to the thin-walled pressure vessels. Pressure vessels are found in many examples, such as balloons. We've got them in pressurized containers. You can imagine your fuselage to be like a pressure vessel, spray can, submarine hull, and so on. So a thin-walled pressure vessel is where we've got 1/10 of the thickness of the radius of curvature is the thickness is 1/10 of the radius of curvature. So if I've got 1/20th, got my diameter there, then I'm going to take that to be 1/20th of that, and that will be, I need to have my thickness less than that value. And so it's falling into plane strain. We're assuming that there can't be any radial stress going off in that direction. When we come to use pressure vessels, we normally work in terms of bar. A bar is roughly the value of 1 atmosphere. 1 atmosphere is 101,325 pascals, so roughly 100,000 pascals. So that's 1 bar. So 1 bar is 10 to the 5 pascals. Notice it's 0.1 of a megapascal. So my pressure vessel I'm going to look at is a cylindrical pressure vessel, and I imagine that there's 2 ways I can try and split the pressure, this pressure vessel. I could either maybe create a split down the side here, or down this side, or maybe at the same time. So some sort of cracking going down the side. I want to avoid the word longitudinal because that is called the hoop stress. The other way that I can imagine that I could crack it, so we could crack it around the circumference here, like this. So we're going to pull it apart. Okay. So pulling it apart relates to stress being applied in longitudinal direction, and making the cylinder come apart in this sort of direction is relating to stress being applied somehow along the circumference. Okay, so it looks kind of, the naming convention looks a bit the wrong way around, because the name convention looks like you're naming the stress in terms of the way that the stress is kind of cracking. It's perpendicular to the crack. You've got to think of the stress perpendicular to the crack. So the crack in this sense is going around here. So the stress creating it is going in a longitudinal sense. The stress is going along the longitudinal of the edge of the cylinder. So the stress is perpendicular, so therefore it is going in a sort of hoop direction. So longitudinal stress, I'm cracking it apart in this direction. Hoop stress, I'm going to crack it apart in this direction. So for the derivation for longitudinal stress, we've first of all imagined that in our cylinder we've got a certain pressure of gas. The gas is trying to push the cylinder apart in all directions, doesn't care which. So it's pushing it apart in all directions, and now for our longitudinal stress, what we're going to do is we're going to imagine that we're going to crack it in half in the direction that we're assuming. So we're basically going to cut through our cylinder. So that means that the force of the gas trying to push it apart will be the amount of pressure inside the gas, and then it's going to be the cross-sectional area that gas is sort of like on either side, pushing either side apart, which will be the internal area in your cylinder. So we've got the pressure times by the internal area of the cylinder. That will be the force of the gas that's applying trying to push it apart. We know forces have to equal one another, so the force of the gas trying to push it apart must equal the force, and now I'm going to go around the edge of my cylinder, and now the structure is trying to keep things together. So the structure here will be around the edge here, and that will be how much stress is being experienced in the thin wall of the structure as it's trying to keep counterbalance the gas inside it. So here we know that the fin wall therefore must be experiencing some stress. We'll call that stress longitudinal stress. What is the thickness of well, rather, what is the area of that wall that's fighting this gas, trying to push it apart? Well, that will be the length times its thickness. So what we're doing is we're imagining that we can model the area for a very thin hoop. Whoops. We're imagining that this can be given as pi d, right? So that's the circumference times by the thickness. So it's as if you got length times by width. Okay, so this is going to be the force then exerted by the structure. So we can say that that this force and this force have to equal one another. Otherwise, these two things are going to be flying apart. So we'll rearrange that, and we'll notice that well, one of our d's is going to end up cancelling. What else is going to cancel? The pi will cancel as well. And then we see that the longitudinal stress for that must be counterbalanced in the structure has to equal the pressure inside the structure times by its internal diameter divided by 4t. What about it cracking the opposite way? Well, in this case, the piece of structure keeping it all apart is, when ignore the ends, is these two lengths. So that's my length there. I've got two of them, and they've got thickness t. So that's the, if I zoom in, that's the area of my structure here, which is keeping things apart. Keeping things together, sorry, rather. And the stress that's being experienced inside there is going to be, we'll call this hoop stress, and so that's sigma h. What about the gas trying to push those two sections apart? Well, that would be based upon the pressure of the gas. Doesn't matter, it's going to be the same everywhere. Times by its cross-sectional area, and that in that case is going to be L times by D. So you can see it's a nice square area. So we've got a rectangle area, so we've got D times L. This case, we can see that the solution becomes independent of L. We'll rearrange this, and we end up with the hoop stress is pressure times D divided by 2T. Now that looks remarkably similar to the previous formula that we derived. So notice the only difference that we can see here is that hoop stress is PD divided by T, and it's times by half, and this one here is PD divided by T, and it's times by a quarter. So of those two stresses, which is going to be the larger one, the half or the quarter? You can see that this will be the larger stress that's been experienced caused by the pressure inside the cylinder. So let's work out, let's do an example, use some typical values we might expect to have. So what's the hoop stress going to be in a 2 millimeter thick pressure vessel? It's 0.6 meters long, it's got an internal diameter of 0.6, and we have 40 bar of pressure inside. Now, so my pressure is 4 times 10 to the power 6. My diameter, why my diameter 0.4? That's not right. So that's not correct. If the pressure is 2 divided by the thickness there, so the thickness is 2 times 10 to the minus 3 there. So that then gives me a value of 400 meganewtons. Okay, so that was radius, I'm guessing, in a previous life. need to be corrected. Right, so 4 to E times by 0.4 divided by 2 times by 0.002. Yes, that's correct. So I need a correction there. Pardon that, fine. So notice that that was the hoop stress calculation there. Notice, compare that to the longitudinal, and that would have half that amount of stress. So where would we expect it to split? We'd expect that the hoop stress to have higher stress be what would be causing the vessel to split. So should it split around the cylinder, split along its length, or split in both axes at the same time? Well, we're expecting it to split along its length there. So here we've got some pressure vessels there. That one looks like it's welded, so hardly surprising. This one here looks like a isometric sort of setup materials. Can't see any sort of welding lines there. My sausages have all split down the side. Okay, my vegetarian sausages. And here we get some perfect examples of my saveloys there, so splitting all the way down the length. So I'm going to go back to those equations I derived for two-dimensional stress, and what I've got there is I've got now I can go for two-dimensional stress. Recall that was given as sigma x over E and sigma y over E there. So recall that we can say that if it's going to go in the longitudinal direction, we're expecting the stress to be related to longitudinal here. So we're taking x to be the longitudinal, and the other stress component is going to be in the perpendicular direction. So that's going to give that equation. So this is just me rewriting those what's called the contravariant stress equations in 2 dimensions, so that they're written in this form here. I can now substitute in what I know what these stress values are in terms of pressure, diameter and thickness of my vessel. So substitute them all in, and then I end up with, well, substitute them in there, and I end up with this set of equations. So for my cylindrical pressure vessel, we've got two things to consider. We've got the strain that's happening in longitudinal strength, strain that's happening in the hoop strength. This therefore tells me how we expect the cylinder to expand, get longer, and then also for the cylinder to get wider with the diameter. Now I know that pi d squared divided by 4 times by L will give me the volume of the cylinder. So these are telling me that I should expect that there should be a change in D, that's going to get bigger, and there's going to be a change in L, that's going to get bigger. So I could use that equation to work out how I would expect the volume of the cylinder to change. I could do that by actually substituting those values in. So if I wanted to, I could just quote the formula from the formula sheet where I substitute those terms in. Alternatively, I could work out the initial volumes and work out the final volumes via the strains and via the dimensions of the cylinder. Okay, so the important thing is that we can calculate the stress in terms of the pressures, diameters and the thickness, and that we're aware that hoop stress is going to be the larger stress than the longitudinal stress. Here's one for you. Okay, internal radius is 0.2, thickness is 2, so we got 4 to the power 6 times by diameter, so that's going to be 0.4. And we're being asked to find the hoop stress, so 2 times by 2 to the minus 3. Okay, so that's going to be 4. What about this case? A pressure vessel, 2 mm thick. Okay, that's the solution. So these are all the pressure vessel formula that I need to use. So it's quite straightforward. Notice that the hoop stress is twice the size of that. Everything else is kind of like just switched around, but we get a different result here for when we substitute in our terms. Hoop is in terms of the diameter, L is in terms of the longitude of the cylinder. So for torsion, when we apply a torque to a component it twists, this type of deformation is called torsion. Torsion can be applied to something that's solid or hollow. It's circular or non-circular members. Torsion in components usually results in the angle of twist as well as shear stress in the wall components. So the torsion engineer's torsion equations we're not going to derive, we're going to say hey ho ho, this looks very similar to a set of equations I've seen before. It looks very similar to the engineer's bending equations, and so we'll learn these just by analogy in terms of the engineer's bending equations. So the first term here in the engineering bending equation, it's about the amount of bending moment that I had applied to my beam to make it bend. This time we're looking at torsion and how things are twisting, so it's the amount of torque, so that's force times distance of how I'm trying to make my shaft twist. Here I've got the second moment of area, but it's not second moment of area, it's the polar second moment of area. So the fact that this is the amount of basically a measure of stiffness, but now it's done in a rotational sense, so slight difference. The formula, the values look very similar, but there's a slight difference. R is always going to be on the outer part of the shaft. It's always going to be the furthest away, so it'll be the outer radius in this particular case. That's where I'm going to get maximum stress, and that will be where I'm applying my torque, assumably. Shear stress will be the shear stress at that location R, so in that case it's going to be shear stress on the outer surface. G is going to be the shear modulus. Okay, theta is going to be the angle of twist. Angle of twist, note, is measured in terms of radians, and L will be the length of the shaft. So here we got L. Okay, something we probably haven't seen before is that if we're looking down at the end of the rod that's been twisted, this is the angle theta at the end. Now if I look down at the other end before the twist and I drew a little line there, and then I've applied the force and caused it to twist around, I could then measure this angle here, this gamma angle, and that will be the shear strain that's being experienced. So the shear strain, so this is my cylinder. So my shear strain is going to be the notice that you could use the small angle theorem. So for example, you could do tan gamma. So you could define it as the path that's been moved around there, I'll call that S, divided by the length of the shaft. So when I apply more torque, I'm going to get more twist. So that's remember that's referring to twist in the sense of looking down the shaft there, and you get a plot which looks remarkably similar to a stress strain plot. And so this linear region, which I made non-linear, is going to be how I measure the modular rigidity, the shear modulus. Unlike the engineer's bending equation, we like to use all the columns. So for example, you might want to look at the shear stress and the twist. So these would be sort of values maybe you want to calculate. You want perhaps you are going to twist it a certain amount and you want to find the shear stress, or we know that the material can take a certain amount of shear stress before it fractures, so therefore you want to find the maximum amount of twist. So that's how you'd use columns 2 and 3. Now the J, the polar second moment of area, is a very similar term to the second moment of area, which we came across in the engineer's bending equations. And indeed, so much so that the equation, you may recall, for a rod type thing, which we was trying to apply some bending on it, is going to give me I is pi divided by 64 d to the power 4. So that's the I value which we'd use in terms of bending a circular rod. However, in trying to twist in it, J becomes pi divided by 32 times d to the power 4. So you'll find this for most terms, that the number in front, whether we're going from something that's been bending or something that's been twisting, will change in terms of I to J. Using the first two columns, well, for example, I might be applying a stress, torque, sorry, that'd be typically what would happen, or we got a torque range and we want to know what stress is occurring, or vice versa. Again, the material has, we know that the materials has a certain maximum shear stress, and therefore we want to find the maximum torque that can be applied. So that's typically what I would want to find for those two columns. Why am I interested in torque? Well, torque relates to the power that a particular shaft can transmit. So if you think maybe a submarines or a helicopters or an aircraft, so these will all have a certain amount of power that they're trying to transmit down the shaft, and that's going to relate to the amount of torque that it can experience times by its angular velocity. So that is T times angular velocity, where angular velocity there is in rads per second. So you need to watch out that your angular velocity is not in RPM, in which case, if it is, then you need to convert it by times it by 2 pi. Remember, revolution is 2 pi, and dividing it by 60. So per minute then becomes per second. So determine the maximum stress in the solid shaft with a shear modulus of 80 gigapascals and a diameter of 100 millimeters and length 2 mil when it twists by 2 degrees. So I'm going to be using the last two columns of my torsion engineering equation. So that one, and that one. Okay, so, or at least I think I am. Yeah, we've got the length there. We got the diameter, the radius. We'll take the diameter and halve it. What else we got? We got the shear modulus. And we're going to be told to use 2 degrees there. So that will give me the maximum stress. Okay, so let's have a look at those values. One thing you've got to watch out for is that when we're converting our theta, sorry, when we're using the theta, we need to make sure it's in radians. So what I'm going to do is I'm going to use 2 pi divided by 360 times by 2 converts that into radians. Now I can substitute those values in. Sleep. Right, wakey wakey in. Right, almost at the end. So it's not only you that fall asleep. So put those values in there. So there's my angle, there's my G, there's my R divided by the length, and then I'm going to get my shear stress. So here's an example for you to try out. So here we will want to use shear stress divided by radius times by G theta divided by L. Okay, so here's our solution. You should have got 13.71. Yeah, so 13.71, so there's the solution. And then finally, how do you work out power? Well, power we relate to torque times omega. So there we have the engineer's torsion formula. There another set formula that we need to use. We do the problem sheets over the next couple of weeks, and that'll be everything done for the course. That's it. I'll stop there.